Today, Paolo Marimon from Technical University Vienna will talk about minimal operations over permutation groups. Please, Paolo.
Thank thank you. And thank you very much for inviting me. Actually, indeed, for inviting me again, because unfortunately, the first time I was supposed to give this talk, I got a terrible fever and couldn't do it. Well, I guess with the time between the previously scheduled talk and this one, we polished a little bit the results. So hopefully, that's going to be nice. And I'm going to talk today about minimal operations over permutation groups. And this is joint work with Michael Pinsker. Okay, so we're going to talk about minimal operations, about permutation groups, and the idea is that we actually managed to get a kind of coarse classification of them, which ends up being quite nice. But obviously, first I've got to cover a little bit of the background about what minimal operations even are and so on. Then I'll be covering our main results, classifying these minimal operations over permutation groups. And then, if we have some time in the end, we'll also discuss how this can help with some questions on of Borirsky, which are related to infinite domain constraint satisfaction problems. Okay. So let's start with just the definition of a clone. I mean, presumably many people here are familiar with it, but the idea is just we work on a set, possibly infinite. I write O to mean like the set of all functions from some power of our domain into itself. And a clone is just a set of functions which contains all projections and which is closed under composition. And for some set of functions S, uh, um, we use this notation to mean just the smallest clone containing S, which is just the clone that is generated by S by closing it under projections and compositions. Okay. And in particular, we're going to be interested in close clones with respect to the pointwise convergence topology. And the idea is just that the notion of closure in this topology, which sometimes it's described as local closure, is that if we have a set of operations S, a function f will be in its closure if for every finite subset of the domain, there is some other function in S that locally on the finite set A agrees with f. And I mean, obviously, when B is finite, this topology just trivializes. So on a finite domain, close clone just means clone. We have reasons to care more about close clones on an infinite setting. But if for some reason you don't like topology, maybe I should say that the theorems that we'll see later actually only work better if we don't have if we just work with clones rather than close clones. But the idea is that this topological closure gives us a notion of generation where basically if we have a set of operations S, we just use this notation to mean the smallest closed clone containing S, which is just obtained by closing S under composition and projections first, and then by taking this local closure operation with respect to the topology. And the reason why we care about close clones is that in general, there is a correspondence between close clones on a given domain and polymorphism clones of relational structures on that domain. So the polymorphisms of a relational structure just functions from some power of that structure into itself that preserve relations. So the idea is that close clones on a domain correspond to kind of high arity symmetries of some relational structure on that domain. I have a thing that I can click if people want to see more about polymorphism clones, but otherwise I'll keep going. Okay. So now let's talk about monorealism.
Excuse me, are we supposed to see your slides? Because I'm just seeing your face. Maybe it's my problem, or does everybody have this problem?
I can see the slides.
Okay.
I can see the slides.
Oh, I can. Okay,
Thank
sorry
you.
about that. I cannot.
I
Maybe
can see the slides.
Zoom has maybe two registers, two tabs that you can swap between slides and
Okay.
a
Sorry about
maybe
that.
you can try something.
Okay.
Thank you very much for bringing this up, so okay. Oh, sorry. I'll keep going, hoping that you manage to solve your issue with seeing the
Yeah,
slide.
it's okay.
No worries. Okay. So if we want to understand clones in a given domain, a way to do it is kind of by splitting this study into looking at monoidal intervals. So say that we have a transformation monoid on B. So, just a set of unary operations containing the identity and closed under composition. Now, closed clones, today we're working with closed clones, with unary operations at the closure of the transformation monoid, form an interval in the lattice of clones on our domain. We call this monoidal interval of T. And now, the study of monoidal intervals, and for example, how large they can get for different kinds of monoids, is a kind of theme in universal algebra that has been studied in various occasions. In Zendre's book on clones in universal algebra, the beginning of chapter 3 is dedicated to this, for example. And for example, if we look at the monoid of all operations in B, the monoidal interval of this was described by Burle. Looking at permutation groups, there was work of Palfi, Zendre, and Kearns, with a particular focus on collapse. So basically, as we said, we have this monoidal interval of clones that contain unary operations, our monoid, in this case, our permutation group on a finite set. And a lot of the research in the context of permutation groups has focused on basically finding conditions, some kind of like strong forms of primitivity, that imply that the interval actually consists of a single element, by which people meant, which is why people call this collapse. We're kind of actually going to go almost in the opposite direction and look at what can be there when we don't have collapse. And then obviously this was also studied for other monoids and over infinite sets, again trying to, for example, describe which kind of monoids can give intervals of different sizes and so on. This is roughly the idea. And now, if we look at the monoidal interval of some transformation monoid, it's reasonable to ask what's the minimal amount of structure that we can find in it. And I guess this is one way in which one can approach the notion of a minimal clone. So if we have a closed clone C, then we say that another closed clone that strictly contains it is minimal above it if there is no other closed clone which is sandwiched between them. And then there is a related notion of minimal operation. But first I'm going to define what it means to be almost minimal, which is going to be an important notion for the rest of this talk. So a K operation F, which does not belong to C, is almost minimal above C if basically whenever I look at functions of strictly lower arity than the arity of K, and what F generates together with C of such strictly lower arity, it just doesn't generate anything new. Okay? So I'm almost minimal when together above C, when together with C, I don't generate any new operations of lower arity. And if I'm almost minimal, and the clone that I generate together with C is minimal above C, then we say that F is minimal above C. So just the idea is simply that F is minimal above C when it generates a minimal clone above C, and it's also chosen to be of minimal arity such that this happens. And now just some basic facts about minimal clones and operations. So first of all, for a clone to be minimal above C, that's equivalent to that clone being generated by C and a minimal operation above C. Again, I'm just going to say generated rather than locally generated, since unless said otherwise, I'm going to assume that we work with this topological closure. Okay, now if we look at minimal elements in the interval of T, which lie above the clone generated by T, where T is our transformation monoid, well, these elements just correspond to minimal clones above the clone generated by T, which are not essentially unary. Or just a function is essentially unary when it depends on only one variable, and otherwise we say it's essential. And we say that a clone is essentially unary if all of its operations are essentially unary. Now, over a finite set, we can always find minimal clones. So, if we have some clone E containing C strictly, we can always find some D contained in E, which is minimal above C. This can fail over an infinite set, but in the setting that we're going to be most interested in, that we're going to talk more about in the next slide, we can still also find minimal operations. However, and this is another nice reason to introduce the notion of almost minimality, I mean, just essentially by definition, we always have that if some clone strictly contains C, then we can find an almost minimal operation in that clone above C. And the objective of, today's talk is that we're going to study minimal operations above the clone generated by a permutation group, in particular a non-trivial permutation group, since the case of a trivial one has already been done, as we'll see later. Okay. Any questions so far? I'm going to take that as a no and proceed. Okay, so I would say, obviously, I mean, it seems worthwhile just per se to try and investigate minimal operations above permutation groups. Permutation groups sound like one of the very first natural monoids one would want to look at when doing this sort of trying to understand monoidal intervals. But some of our original motivation actually comes from infinite domain CSPs, and in particular oligomorphic permutation groups. So I'm just going to have one slide where I'm talking slightly less of universal algebra. I'm talking a little bit more about oligomorphic permutation groups and CSPs. The idea is, as I was saying, so some of our motivation comes from infinite domain CSPs. So a CSP is just a computational problem where we're given a structure B, which is a template, and then for some, we are looking at the computational problem where we're given some finite structure A in the same language, signature, and we're asking whether there is a homomorphism from A into B. I imagine you've seen many talks about CSPs in this seminar, but if someone would like a refresher, I'm happy to go through it. I mean, I have a button for it. And I mean, people study a lot finite domain CSPs, but where I was coming from was looking at infinite domain CSPs, where a class that is particularly studied is that of omega categorical structures, which are characterized by essentially having an oligomorphic permutation group. So a structure has an oligomorphic permutation group if it's has an oligomorphic automorphism group if its automorphism group has finitely many orbits on n tuples for each n, and our structure is countable. So these are also known as omega categorical structures, just by a theorem of Rilnat-Zersky. Oligomorphicity of the automorphism group corresponds to the first order theory of our structure having a unique countable model up to isomorphism, which is called omega categoricity model theory. And so some basic examples of omega categorical structures are just a countable set with equality, or the rational numbers with their order, or the random graph. But the idea is just that when people look at infinite domain CSPs, we can somehow reduce to a context which is exactly what we're trying to look at from the point of view of minimal operations about permutation groups, is we can always show that we can always reduce the case of our structure B being a core, so such that the closure of its automorphism group is just its endomorphism monoid. And we also know that if the polymorphism clone of B is essentially unary, so only has essentially unary operations, then the CSP of B is hard. So when we're studying CSPs of omega categorical structures, since we already know how to deal with the essentially unary case, and we can always essentially find a homomorphically equivalent structure, which is a core, we can work under the assumption that our polymorphism clone strictly contains the clone generated by the automorphism group of B, and also that the unary operations in this polymorphism clone are just the closure of the automorphism group. Okay? But then in this context, since here we have a strict containment, with the additional assumption that our structure is in a finite language, we can always find some minimal operation in the polymorphism clone above the permutation group given by the automorphism group of our structure. And I mean, this is obviously going to be of arity greater than 1, since we already know that all of the unary operations are just the closure of the automorphism group. And this is very important to understand these minimal operations. There's basically a lot of arguments in infinite domain CSPs where they try and prove some kind of like complexity dichotomy for a certain class of omega categorical structures. Those arguments really rely on finding some low arity, in particular some binary essential polymorphism, given the existence of an essential polymorphism. And so it's helpful to develop tools to understand when we can find binary essential polymorphisms in our polymorphism clone of an omega categorical structure. Okay, so apologies for this digression into CSPs and oligomorphic permutation groups, but I just wanted to kind of clarify this other motivation, and we are going to encounter oligomorphicity quite a bit later. Okay, so before we can talk about what it means to classify minimal operations, it might be good to talk a little bit about what kinds of operations we might be thinking of and how we're going to describe them in terms of identities. So I use this approximation symbol to actually mean an identity that holds globally. And for example, quasi-majority is just a ternary operation such that whenever I have like 2 x's and maybe 1 y in my inputs, then I'm going to be equal to m of xxx. And similarly, a quasi-malsev is defined by this other identity over here. And here I have the term quasi. And what's going to happen is that when f is idempotent, so f of xxx is equal to x always, then we remove the term quasi. So for example, if here we had that m of xxx is equal to x, then this would just be a majority. And similarly, if we had this here. And for example, here we have a ternary minority, which compared to the majority, instead, when we have 2 y's and 1 x, it selects m of xxx, and it also equals to x. And then a quasi-semi-projection. Well, what happens in a quasi-semi-projection, a k-aric semi-projection, is that there is some I between 1 and k, and some unary operation G, such that whenever I look at a non-injective tuple, so a tuple where at least two elements are the same, then f of that tuple is going to be equal to G of AI. So it's kind of going to project to AI whenever two elements in the tuple are the same, up to a unary operation. And again, if we remove the quasi, then obviously we don't have the unary operation, and we just get that whenever f is evaluated in a non-injective tuple, then it equals to AI. Okay. Now, there is a classical theorem of Rosenberg that classifies minimal operations above the trivial group, right? So this would be just minimal operations above the clone generated by projections on our domain. So Rosenberg's theorem just says, well, if P is finite and F is minimal above the clone generated by the identity, then it can only be of 5 types. Well, a unary operation, a binary operation, a ternary majority operation, a minority of the form x plus y plus z in some Boolean group, where a Boolean group is just a group where every element has order 2, right? So an elementary abelian 2 group. And finally, the 5th case is that of a k-ary semi-projection for some k bigger or equal than 3, and obviously bounded above by the size of B. Okay. I mean, this is a wonderful theorem. Except for the case of a minority and a unary operation, we don't really have a full characterization of cases 2, 3, and 5. So, I mean, later research and current research kind of tries and describe more carefully what a ternary majority, which is minimal, has to look like. And I also now wanted to just talk 1 second about another result above some permutation groups, which was previously obtained. So Borirsky and Chen, I mean, as I was saying, there is some motivation coming from oligomorphic permutation groups and infinite domain CSPs, classify minimal operations above oligomorphic permutation groups. And so you say, well, if G is an oligomorphic permutation group and F is minimal above the clone generated by G, then F is either unary or binary or a ternary quasi-majority or a k-ary quasi-semi-projection where K is bounded above by 2 times the number of orbitals of G minus the number of orbits. So an improvement, I guess, here, well, our majority turned into a quasi-majority and our semi-projection turned into a quasi-semi-projection, but we also don't have any minority type of operation. Now, what we're going to do is actually classify minimal operations in a similar way, but above arbitrary permutation groups. But something good to keep in mind is that we actually also improve also this case in ways that is actually helpful to do stuff on megacategorical structures. Okay, so this is our main theorem. We look at G acting on B, a non-trivial permutation group with S many orbits, where again, we allow B to be finite or infinite, we allow the number of orbits to be finite or infinite. And we take a minimal operation above the clone generated by this group. There are only going to be 4 possibilities for F. The first 2 are just a unary or a binary operation. And then moving on to the higher rarity operations, well, we have the quasi-minority case, where our operation is going to be of the form an element of G composed with M, where M is this thing which we're going to explain later, which is a G-invariant Boolean Steiner 3 quasi-group, which actually is a strengthening of x plus y plus z on a Boolean group. Like it satisfies that and actually even stronger conditions. But in particular, this only happens when G itself is a Boolean group acting freely on B. So this third case, I mean, essentially it never occurs. I mean, it will occur extremely sporadically because not only we're asking that G is a Boolean group, so, you know, elementary, every element has order 2, but also we ask that the action is free, right? So that fixing an element means that you are the identity. And then the final case strengthens the assumption of quasi-semi-projection, and we say that F is a k-ary orbit semi-projection. So again, we're going to define this more carefully later, but the idea is that we act as a semi-projection, but not just whenever two elements are the same, but whenever two elements are in the same orbit. And so because of that, the arity of F is actually bounded above by the number of orbits, not only by the number of orbitals, like in the previous theorem of Podilsky and Chen, for the restricted context of oligomorphic permutation groups. So if you paid attention, which, I mean, hopefully is the case, you can notice that there are no quasi-majorities in this classification. So the moment that you have like any amount of symmetry, I mean, in this group case, of course, the possibility of a quasi-majority is destroyed, which is kind of curious. And as I was saying, in the context of oligomorphic permutation groups, our result is a good improvement on the theorem of Podilsky and Chen. So first of all, the action, like an oligomorphic action, is never going to be free. So we're not going to have this case. So we're only going to have 3 cases. And now, instead of having a quasi-semi-projection, like in the theorem of Podilsky and Chen, we have this orbit semi-projection, which is a stronger assumption, and we have a better bound on the arity of our semi-projection. I mean, something I think is just nice, that I think is worth saying is, and I don't know, this is something that I really like about this theorem, is that it's a non-trivial theorem, I hope, which is true for every non-trivial permutation group, but it's false. It is also going to be false for the trivial group, where we do get a majority case. Okay, but now I promised that I would explain what these higher arity operations are, and I better do that in the next couple of slides. Any questions, by the way? I'll keep going, so maybe you have questions after you know what the operations look like. Okay, so we had this operation which was a G-invariant Boolean Steiner 3 quasi-group. So we got a lot of words to explain. So let's start with a Steiner 3 quasi-group. Well, this is a symmetric ternary minority operation which satisfies this condition. So what does this condition tell us? Well, it tells me that if I have x, y, and z, and I look at w, which is just m of x, y, z, I also have that z is equal to m of x, y, w. And we also get that x is equal to m of y, z, w, and y is equal to m of x, z, w. So the idea is that we can actually draw a kind of blob around these 3 points that just tells us that whenever we pick 3 of these points, the 4th point is going to be m of the other 3 points. And, you know, if we keep taking these blobs of 4 points for all 4 tuples of distinct elements for which we have this property, well, obviously, just because of the fact that we have a function, we're going to have that every 3 points are going to be contained in exactly one set of 4 points. And I mean, this has a specific name. What we get is a Steiner quadruple system. So for a hypergraph, or I mean, you can think about this as a set with blocks of 4 points. such that every 3 vertices are in a unique 4 hyperedge. And standard 3 quasi-groups just correspond to standard quadrupole systems on the domain. And these have been heavily studied in universal algebra and in connection with design theory. Now, let's add Boolean. When we are Boolean, we are a standard 3 quasi-group. In addition to the previous conditions, we also satisfy this other identity. So this tells me that if I have x and y, so you have 2 4 hyperedges with a common pair of points, and then I look at the remaining 4 points, then this actually implies that there is a hyperedge between the remaining 4 points. And this condition is actually equivalent to M being of the form x plus y plus z on a Boolean group. Again, this was also previously studied in universal algebra. The new condition that we get out of minimality over a permutation group is this invariance condition. So the idea is that whenever we have our operation and we try and twist each element in our minority by some group element, we can just move all of those group elements outside. And what this actually tells us after a little bit of thinking is that our minority not only induces a Boolean standard 3 quasi-group on our domain, but it also induces this on the G orbits. And this is very helpful because then it actually gives us, after some more study, necessary and sufficient condition for the existence of a G-invariant Boolean standard 3 quasi-group. So basically, if G acts on B, there is a G-invariant Boolean standard 3 quasi-group. If and only if, well, G is a Boolean group acting freely on B, but also it has either 2 to the n many or infinitely many orbits. So this, as I was saying, these minimal operations appear extremely sporadically, only on 2 to the n many orbits for some m or infinitely many orbits. And again, we need the group action to be extremely specific. Now, something that happens more ubiquitously instead is this orbit semi-projections case. So as I said, an orbit semi-projection is essentially just a semi-projection, but when 2 elements are in the same orbit, rather than just literally being the same. So I'm an orbit semi-projection if there is some I and some element in the closure of my group, such that whenever 2 points in my tuple are in the same orbit, I collapse to G of AI. And now, kind of following ideas of Palfi, we studied the existence of semi-projections in the context of Rosenberg's theorem. We can prove that, for example, on a finite domain, for any k between 2 and the number of G orbits, there is a k-ary orbit semi-projection minimal above the clone generated by G. I mean, of course, here the bar above the G is redundant since we're on a finite set. This is also true in the context that interests us most, which is that of oligomorphic permutation groups, where these are the automorphism group of some megacategorical structure in a finite language. Again, we get exactly this lemma. Another thing maybe worth pointing out is that earlier I was saying, well, if you don't like topology and want to just look at minimality in the lattice of all clones, which is a different notion of minimality, but defined in the same way, then actually exactly this construction will give us that for arbitrary group actions, there is a k-ary orbit semi-projection minimal in this different sense of minimality above the clone generated by G without the closure operation, without the topological closure, sorry. But I mean, I'm going to ask this as a question in a second. When we look at the topologically close clones, it looks like in the infinite setting, the situation might be a little bit more complex. But at least when we look at almost minimal carry orbit semi-projections, I mean, actually, it's easy to see that any essential orbit semi-projection is always going to be almost minimal, and we actually are going to have that they always exist. But a problem that I think we even have in the archive version is that, I mean, it's possible, and I actually think it's probably true, that there is some group action on an infinite set that has 3 orbits but no ternary orbit semi-projection, which is minimal above the clone generated by the group. Somehow, the addition of this closure operation in this particular context complicates the picture quite a bit. So it's quite easy for some candidate orbit semi-projection to prove that it's not minimal, but it's quite difficult to think of a scenario where one can prove that there is not going to be any minimal one, especially because they're always going to exist as almost minimal. Okay. So I described this G-invariant Boolean standard 3 quasi-groups, and I described the orbit semi-projections. Now I'm going to talk just a second about the methods that we use. So we actually don't only classify minimal operations. We actually classify almost minimal operations above permutation groups. And this classification splits into 3 cases. That of not having a Boolean group acting freely on B, that of a Boolean group acting freely on B, but with more than 2 elements, and that of just Z2 acting on B freely. Okay, I'm going to just drink a tiny bit more. Any questions for the moment? Okay, so when we classify almost minimal operations, in the case where we don't have a Boolean group acting freely on B, and we're classifying almost minimal operations, again, just in the case of minimal operations, we only get three cases. So to some extent now we're classifying in the same way a much larger class of functions than minimal ones. And again, we just get unary, binary, and carry orbit semi-projection. So kind of same kind of description that we would have for the minimal operations. But in this case, when we're looking at almost minimal, any carry orbit semi-projection is going to be almost minimal, and they always exist as long as we have enough orbits. When we look at a Boolean group acting freely on B, and of size greater than 2, the only extra case that comes up is a minority case, a quasi-minority case, but it doesn't get to be as strong as that of a G-invariant Boolean standard 3 quasi-group. So we call this just a G quasi-minority, and the idea is just that basically whenever I have M of Y, X, and X moved by a group element, then I end up selecting Y and twisting it by that group element. So this is kind of how this G quasi-minority works. So it's going to be a quasi-minority, but we can also describe how it acts on the orbits, which is, I guess, a feature of how we run these classifications of minimal and almost minimal operations. And then the case of Z2, so the binary operation case actually disappears. You can't have a binary minimal operation above a clone generated by Z2 acting freely on a set. And we get these 2 things, an odd majority and an odd malsev. So an odd majority is a majority and an odd malsev is an odd majority is a quasi-majority and an odd malsev is a quasi-malsev. And they're kind of dual of each other. So an odd majority generates an odd malsev, and an odd malsev generates an odd majority. And for example, an odd majority is defined by being a quasi-majority and then satisfy this other strange identity, which says that whenever I have Y and X, and then the other point is twisted by the identity, by the element which is not the identity in Z2, then I select Y, Y, Y. But I mean, obviously, since they don't feature in the other theorem, one can prove that majority and Maltsev operations cannot be minimal. Actually, when I was going to give the talk the last time, I had just proven this. So I had like several pages where I was trying to figure out what a minimal majority had to look like over Z2. And then I kind of lost a friend realizing that they couldn't exist after weeks of thinking about it. But I mean, I guess the theorem looks nicer anyways after that. So, okay. So we have all of these nice classification theorems. What can we use this kind of results for? So something that we can use this for is to answer some questions of Borirsky on infinite domain CSPs. So now we have a copy of the paper on the archive, and probably we'll put a newer version soon as well. But there we answer 3 questions of Borirsky. Today we're just going to answer one, which is the most relevant to this particular project of classifying minimal and almost minimal operations about permutation groups. And as I was saying earlier, it's important in the context of CSPs, in particular infinite domain CSPs, to find some kind of binary essential polymorphism given the existence of some possibly higher arity essential polymorphism. And this is like just constantly used in every dichotomy in an infinite domain. And so there is this question of Borirsky in his book on infinite domain CSPs, which says, okay, so say that B is omega categorical and it's a core, so the closure of its automorphism group is equal to the endomorphism monoid. And our polymorphism clone has an essential polymorphism, right? So something that is not essentially unary. Can we find a binary essential polymorphism? So the answer to this is actually very much no. And I'm going to give the example in a second. But I should also say that it's also like true whenever the automorphism group of our structure has less than 2 orbits, right? Because, well, we're going to have that pole B has some operation F almost minimal above pod B. And now, since we have less than 2 orbits, we're not going to have the possibility of some carry orbit semi-projection of arity bigger than 2. So our operation actually has to be binary. And so, if we have less than 2 orbits, the answer to this question is very much yes. In the case of more orbits, the answer is no, just because actually, if you pick any oligomorphic permutation group, any omega categorical structure, with more than 3 orbits, then we can find some other omega categorical structure, B prime, such that its polymorphism clone is just generated by the automorphism group of our original structure, and F, some kind of S-ary orbit semi-projection, where S is the number of orbits of our automorphism group. And so here, the orbit semi-projection is going to be an essentially S-ary polymorphism, but we don't have any essentially polymorphism of lower arity than that. So I mean, this is the counterexample to the question of Borirsky. However, and I mean, obviously, this is again a core in this sense, just because the unary operation is going to be the topological closure of the automorphism group. But it's important to understand that actually there is a very variable kernel of truth in this question of Borirsky, not just because of the silly trick about when the action has less than 2 orbits, but also precisely in the context where we're studying CSPs. So suppose that we have a finite or omega categorical structure, which is a core, and such that its automorphism group is not in the Boolean case, right? So we don't want a free action of a Boolean group on B. Again, this is always satisfied if B is omega categorical. Now suppose that the polymorphism clone of B does not have a uniformly continuous homomorphism to the clone of projections on a two-element set, right? But just uniform continuity just means that there is some finite subset of B such that if two functions agree on that finite subset, then they're sent on to the same function. In this case, it's the same projection. Okay, so we have these assumptions, right? So we are in the case of essentially most non-rigid structures which are finite, or any omega categorical structure. And we don't have a uniformly continuous homomorphism to the clone of projections. Well, then we can deduce that the polymorphism clone of B contains a binary essential polymorphism. Why is this the case? Well, first of all, just a couple of observations. One is, why is this important for CSPs? Well, this condition star implies that the CSP of B is NP-hard. So for the purposes of infinite domain CSPs, if we want to run some kind of dichotomy argument, well, we're going to know that if we don't have a binary essential polymorphism, we're going to be NP-hard. So we may assume that we do have a binary essential polymorphism when we're doing this kind of complexity classifications. So this is quite helpful for that. And essentially, like, this just avoids lots of like previous more ad hoc arguments that we're trying to find binary essential polymorphisms given some essential one. And just I'm going to give a quick sketch of the proof, which is just supposed by contrapositive that we don't have any binary essential operation, right? So then if we intersect our polymorphism clone with the binary operations, we're just going to have whatever is generated by the automorphism group and in terms of binary operations. So we're only going to have essentially unary binary operations, right? So in this case, since we don't have any binary operation except for the ones generated by the automorphism group, every ternary operation in, I guess, here I should have written PolB, is going to be almost minimal. So in particular, every element in PolB is either essentially unary, or it's going to be an orbit semi-projection. And now, just reflecting on orbit semi-projections, it's relatively easy to see that they only satisfy trivial identities. And so this actually allows us to build a uniformly continuous homomorphism to the clone of projections. Indeed, we can actually prove, and actually, I mean, this is not yet in the archive version, but it's going to be soon, that for any permutation group, if we look at the clone generated by the group and all orbit semi-projections, then that has a uniformly continuous homomorphism to the clone of projections on a two-element set. So we also get this. Okay, so this is my talk. So thank you very much. And yeah, I mean, I hope you found this enjoyable. Obviously, we have extra times, which is always good if you have questions. Here is the funding statement. Here's your little very cute people holding hands in the PALS website, which I thought of adding. And I mean, I also have a bunch of slides of biography and extra things that people wanted to ask. But I mean, hopefully people have some feelings or thoughts or questions. And thank you very much again.
Thank you. If you have some questions for Paolo, please just